All right. So this is now the third video in the series. Now, for the past two videos, what we have been doing, and for the past week, what we have been doing is something called taking the limits, right? Now, there's an important thing that we will discuss right now, and that is the concept of instantaneous change. How does your car, for example, know what speed you're doing at that instant? How does it know that you are speeding, right? Because in reality, what you need to have are two specific points of time. Then you consider how far apart are you in those two pieces of time, how long are those two pieces of time to how long in between those two pieces of time. So then you can calculate distance over time, and then you have an average speed. But think about instantaneous change as change that happens at an instant. The difference between the two periods of time is very, very small. Now, in this graph right here of a certain function, let's call this function f of x, right? Where we indicate a certain point. So this is a point a f of a. What we want is to find the slope of this tangent line here. The goal is to find the slope of the tangent line in this example, right? Because slopes, if you recall, slope, the way we get slope is this is change in y over change in x. Now, as of right now, uh, we can try to calculate the slope of this line directly, but the way we're gonna do this is convoluted. So this is our goal, right? The way we're gonna do this is we're gonna take, so from this graph right here, we're gonna take a second point, right? So let's call this b f of b. Then we connect these 2 points right here and create a line, right? Now, for this particular line right here, we can calculate its slope. How do we calculate its slope? Again, slope is equal to change in y over change in x. So, what are the y's that are changing? In this case, f of b and f of a. So, f of b minus f of a all over change in x, which is b minus a. All right. So, this is the slope of the secant line. Okay. When we say secant line, that means that the straight line hits 2 points. Okay, in this case, this point and this point. Then you can imagine that we move the point ever so slightly closer to A. So we're going closer and closer to A to have a new B and a new f of B. And we will have a new line with these 2 points right here. Now, you can imagine that this right here, we're getting closer and closer to A. And then, if you can imagine, this point right here stays, then but this point right here moves towards here, f of A. And in each of those points, you define a line. Okay? So it starts from here. Then you can imagine it moving here, then here, towards to the point where it becomes. So imagine these 2 points right here. This defines a line. Then you keep on moving, though this point here, this point on the red one stays here. So imagine this defines a line. If you go closer, this defines another line. And you keep doing that, and you see that you will create a family of lines up to the point where it just hits 1 point. So tangent line here means it hits 1 point. Okay, that's what a tangent is, right? Now, on the other hand, what does this mean? On the other hand, this means if, for example, your point is here, let's say B is there, and f of B is here. So you have those 2 points. You define another line, okay, right? So I'm an imperfect line drawer. By the way, I've also included an applet where you can do the sliding by yourself. But for this video, indulge me. And the way we do it is this point right here stays, but this point moves towards A. Okay. So you can define another point here. Okay. And you can imagine that this, like before, this goes closer and closer and closer and closer to A, this time from the right. Oh no. But the calculation for the slope is the same. The slope of this line, of the secant line, is still change in y over change in x, which is equal to f of b minus f of a over b minus a. But, technically, it can be f of a minus f of b all over a minus b. These are the same, right? So, we notice that in each of those lines, the slope is always this number right here. And what is the action that we're doing? What we're doing is we're approaching we're approaching A from the right, and also in this example, we're approaching B from the left, approaching it this way. Is there a concept that we have discussed that involves dot? The answer is yes. So if we then try to find the limit as B approaches A, okay, of f of B minus f of A all over B minus A, right? If we try to find the limit, so we can read this as the limit of the slope of the secant line as B goes to A from both sides, because this is a two-sided limit. From both sides, this would be equal to what we call the derivative on A. Or we read as f prime of A. This is otherwise known as the derivative of f substituted in A. Okay? Or, so the limit of the slope of the secant line as b goes to A from both sides will be equal to the slope of the tangent line at x equals A. This, ladies and gentlemen, is what we call the limit definition of a derivative. What a limit definition of a derivative is in what a derivative is in essence is it tries to find instantaneous change. It tries to find the change at that certain period, at that instant. Okay? But of course, instead of using b, what we do is we use the general variable x. So we then say f prime of x is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Okay? So this is the limit definition of derivative. Okay? Now, as a note, there are different ways to write der- derivative of f, a derivative of f. Okay? So there, in fact, technically there are two ways, right? In two general ways. So this is the first way. So this is f prime of x. Okay. So f prime of x. So this means derivative of f. Okay. Another way would be this. Okay. So we call this here the derivative operator. Okay. So when we see this notation right here, or sometimes it's even written as this, okay, uh, this means this is an indication that you need to find the derivative of f. Okay, this tells you to find the derivative of f. Right? By the way, why is it called d? Why is it d? D is essentially delta. Meaning delta is change. So in essence, this is change in f all over change in x. Or in otherwise, change in y all over change in x. What is that? That, my friends, is the slope of the tangent line. Okay? These notations, by the way, these are from Leibniz, which is who was a German mathematician philosopher in the 1700s, who, with Newton, independently formed the basis of calculus. Newton's notation for the derivative was this. So this is Newton's notation. It didn't really catch on, but it's kind of cool. But in any case, it's these two are the notation for derivative. So again, this is the limit definition of a derivative. This are the ways to find the derivatives. To write a derivative. So let's do an example. What if use the limit definition to find the derivative of x squared plus 1 equals fx. All right? Now, that means that we're trying to find f prime of x, which is again limit as x approaches a of f of x minus f of a all over x minus a. Right? Now, this means limit as x approaches a. What is f of x? It's x squared plus 1 minus. What is f of a? Well, f of a is, well, f of a is you substitute a to the x here. So you get a squared uh, plus 1. Right? If we substitute a to x here, we get a squared plus 1 instead of x squared plus 1. Okay, good. Over x minus a. Okay? Now, let's simplify this. So this becomes x squared plus 1. We distribute the negative here, carefully, of course, minus a squared minus 1 all over x minus a. These cancel out, 1 minus 1. So we're going to be left with limit as x approaches a of x squared minus a squared all over x minus a. Okay? It seems that we are hopeless at this point, but I imagine that this point in the solution is the most satisfying because that means that you can cancel out. So what happens here? Notice, notice that x squared minus a squared is actually a difference of two squares, which is equal to the product of their difference and the sum. Okay, because it's a difference of two squares. So this becomes, so x squared minus a squared becomes x minus a times x plus a all over x minus a. And then you can cancel them out to get the limit as x approaches a. Huh, okay. All right. I needed to pause a bit because what I did, I skipped a step. I skipped a step. I skipped a step. Right. We're gonna revisit this. Wait, I skipped a step. All right. So this is our limit definition, right? And uh, this is fine. Okay, this is totally fine. Right? This is totally okay. But what I meant to say is from this limit definition right here, So we have the limit as x approaches a of f of x minus f of a all over x minus a. Okay. The way that we're gonna rearrange this so that it looks better is this. Let h be equal to x minus a so that becomes x minus h. So you can think of uh, h as how close h is, how close your point is from a. Okay. Now, using this labeling, we can rewrite this into limit. So if x approaches a, all right, if x approaches a, that means that this is the same as x is approaching a, right? So this is the same as h approaching 0. Because if h equals x minus a, and a approaches, and x approaches a, so this becomes a minus a. So at that point, h is a minus a, which is 0. Okay? The denominator becomes h, all right? And the numerator is, so this is f of x minus f of a, which is x minus h. F of x minus h. Okay? These two are equivalent, but this, I stand corrected. This right here is the limit definition of derivative. Dot final. Okay, so I think I need to cross it out. Not final. See next page. So in our problem earlier, so as an example, use the limit to find the derivative of f of x equals x squared. We used x squared plus 1. Okay. So if you're asked to use the limit definition to find the derivative, you use this definition. So that what happens is it becomes the limit as h approaches 0 of f of x, which is x squared plus 1, minus f of x minus h, right? So f of x minus h, what's that? Where, well, what we do is, what you do is, you expand, you input x minus h, take the entire thing instead of just x. So this becomes x minus h squared plus 1. Okay? It becomes this, right? All over h. Okay? Then you do some expansion. The red part here is x squared minus 2xh plus h squared plus 1 all over h. Okay? Now, we can do some simplification. This x squared and this x squared gets cancelled out. X squared minus x squared. This one and this one gets cancelled out. What remains is this becomes the limit as h approaches 0 of h squared minus 2xh all over h. Okay? And notice that from here, what we can do is we can factor out 1h in the numerator. It becomes h times h minus 2x. Sorry, it's not minus 2x. The reason being is this is negative times negative. This becomes positive. So h plus 2x all over h. And of course, they cancel out. This becomes the limit as h approaches 0 of h plus 2x, which we can solve easily, right? H approaches 0, so this becomes 0. And finally, the final answer is 2x. Okay? Actually, we would have the same answer here. We would get 2a, right? In the original expansion. But there's another step that we need to do, and we need to switch a with x, because these are variables after all. These are just variables. So that what you want is something that looks like this. But again, this is a much more cleaner solution, right? Let's do another. Let's do another. So let's try to find the derivative of, let's say, 1 over x using limits. Okay? So, calling this our f of x, f prime of x then is equal to what? It's equal to, well, the limit as h approaches 0 of f of x minus f of x minus h all over h, which is equal to the limit as h approaches 0 of f of x, which is 1 over x, minus f of x minus h, which becomes 1 over x minus h, right? Because again, we are inputting this into the function. Okay? Whatever the function is, whatever all of the x's in the original function, we change them to x minus h. Then this becomes all over h. This is equal to the limit as h approaches 0 of, you can simplify it using your favorite method. Right? So the way I do this is using what we call a butterfly method. I multiply this side to get x minus h. I multiply this side to get x minus to get negative x. Then the denominator is just the product x times x minus h. Then of course it's all over h. After simplification, this becomes the limit as h approaches 0. The numerator is just negative h. Then there's an x times x minus h here. And then of course the over h here just becomes the denominator. It just resides here somewhere. Okay. Then noticing that we can cancel these out, we're gonna finally get the limit as h approaches 0. We can cancel them out. So the numerator is just negative 1 over x times x minus h. Then from this point, you notice that if h is 0, it becomes that. So now the final answer is negative 1 all over x squared, or negative x to negative 2, which is important for the next lesson. Okay. Both are equal, by the way. All right? Let's do one last example. Let's do one last example. Find the derivative of 6x plus 7 equals f of x using limits. All right, that is not a hardship. Again, this is equal to this limit right here. So then we simplify, this becomes 6x plus 7 minus 6 times x minus h plus 7. Guys, it's safest if you use these parentheses. Don't just write it like this. Minus 6 times x minus h plus 7. No, 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 no. Do not write it this way. Not right. Don't write it down. Don't write it like this. Always include the brackets. All over h. So 6x plus 7 minus 6x minus 6h plus 7 all over h. Then you can't distribute. Okay, of course, you can. But let's bun that. And what do we get? 6x minus 6x, they cancel out. Boom, boom. 7 and 7 here. 7 minus 7, they cancel out as well. So what remains is negative 6h, which is positive 6h. So I'm just going to write 6h all over h, which is the limit as h approaches 0 of 6, which is equal to 6. So the derivative of 6x plus 7 is just 6, which makes sense because if you think about it, this is just a line. So anything tangent to it, it's just going to be that line, you know. So yeah, for this video, we discussed what the limit definition is and what is the motivation for this lesson, for what a derivative is. Okay, you might be wondering, sir, uh, if I have a harder function, quote unquote harder function, am I always gonna use the limit definition? Am I always gonna do this? The answer in the next video. Bye for now.